Consider for a moment a cup of tea. You have made it countless times. The kettle boils, steam rises, you pour the water over the leaves and wait. In a few minutes, you drink something pleasantly warm. An hour later, that same cup sits forgotten on your desk. Room temperature. Unremarkable. No longer capable of warming anything at all. You have just witnessed the fate of the entire cosmos. This is not a metaphor. It is not poetry dressed up as physics. It is a preview, a miniature demonstration of what awaits every star, every galaxy, every atom in the observable universe. The cup of tea cooling on your desk operates by precisely the same principle that will determine whether the cosmos ends in fire, ice, or something stranger still. We find ourselves in a bewildering universe, 14 billion years old, stretching across 93 billion light-years of observable space, containing roughly 2 trillion galaxies, each home to hundreds of billions of stars. The numbers defeat imagination. We cannot picture 2 trillion of anything, let alone galaxies. And yet, for all its unfathomable grandeur, this vast cosmic machinery is running down. Every star that burns is spending fuel it cannot recover. Every galaxy that shines is paying a debt it cannot repay. The universe, it seems, is a cup of tea that has already been poured. Here is the strange thing, the thing we somehow fail to notice despite experiencing it every day of our lives. Hot things cool down, warm things reach room temperature, energy spreads out, disperses, becomes ever more evenly distributed until there are no differences left to exploit, no gradients remaining to power any process whatsoever. This is not a tendency, it is not a preference, it is a law, as fundamental as gravity, as inescapable as mathematics. Physicists call it the second law of thermodynamics. But you do not need to remember that name. You need only to remember what it means. The universe moves inexorably toward equilibrium, toward the even distribution of energy, toward a state where nothing interesting can happen anymore. Your cooling tea demonstrates this in minutes. The cosmos will achieve it in aeons. But here is where we make our error, an error so natural, so deeply embedded in human cognition that most of us never notice we are making it. We look at the night sky and see permanence. The constellations that guided our ancestors still wheel overhead. The stars that inspired ancient myths still burn. We assume, without quite realizing we assume it, that the cosmic furniture is fixed. The ancients called the heavens eternal. Even modern minds, equipped with telescopes and spectroscopes and all the apparatus of scientific astronomy, secretly believe that the universe will go on much as it always has. Vast, luminous, endlessly interesting. They are mistaken. Profoundly, irrevocably mistaken. What appears permanent is merely slow. Consider the sun. It has been burning for 4.6 billion years and will continue for roughly 5 billion more. To creatures who measure their lives in decades, this seems effectively eternal. But 5 billion years is not eternal. It is merely large. And the sun is merely one star among hundreds of billions in one galaxy among 2 trillion. All of them burning through their fuel. All of them paying the same thermodynamic price. The universe is not a stage upon which human dramas unfold. It is a fire, and fires go out. This realization changes everything, not just our astronomy, but our philosophy, not just our understanding of the cosmos, but our understanding of what it means to exist within it. If the universe is eternal, if stars burn forever, and galaxies shine without end, then perhaps individual moments do not matter much. There will always be more moments, more stars, more light, But if the universe is temporary, if the cosmic fire is even now burning through its finite fuel, then every moment of complexity, every instance of starlight, every cup of tea that is still warm enough to savour, becomes precious in a way that eternity could never provide. The stakes, in other words, are not merely astronomical, they are philosophical, they are personal. Why does the universe go to all the bother of existing if it must eventually cease to exist in any meaningful sense? What does it mean to strive, to build, to love, to think, if all of it, and all evidence that it ever happened, must ultimately dissolve into equilibrium? These questions cannot be answered by looking away. They can only be answered by looking directly at what physics has revealed, and finding, against expectation, that the truth contains its own strange consolation. But first, we must understand why we missed this in the first place. Why do we mistake long for forever? What is it about cosmic time that defeats human intuition so completely? The answer lies not in the stars, but in ourselves. Here is a number, 1 billion. And here is another, 1 trillion. If you are like most people, indeed, if you are like any person who has not specifically trained themselves otherwise, both numbers feel roughly the same. They both register as incomprehensibly large. They both exceed the capacity of ordinary imagination. They both collapse into the mental category of very, very big. And yet, a trillion is 1,000 times larger than a billion. If you counted one number per second, reaching a billion would take you approximately 32 years. Reaching a trillion would take you 32,000 years, longer than all of recorded human history. We have a name for this cognitive limitation. We call it scale blindness. Our brains evolved to track things that mattered for survival on the African savanna. The number of lions in the tall grass, ideally 0. The number of edible fruits on a tree, ideally many. The number of days until the seasonal rains, ideally not too many. We developed an exquisite sense for quantities up to about 7. Beyond that, we begin to approximate. This served us well enough for 2 million years of human evolution. It does not serve us well when contemplating the cosmos. The sun will burn for another 5 billion years. The universe has existed for about 13.8 billion years. The time until the last stars die is approximately 100 trillion years. These numbers arrive in our minds and immediately collapse. They all feel like forever because they all exceed our processing capacity by roughly the same astronomical margin. But they are not the same. They are not even close to the same. The sun's remaining 5 billion years sounds eternal to us, but it represents only 0.04% of the time until the last stars fade. What we perceive as cosmic permanence is merely the opening bars of a symphony that will play for aeons and then fall silent forever. We make this error because we must. Our brains were not built for this. Just as we cannot perceive ultraviolet light or hear frequencies above 20 kilohertz, we cannot intuitively grasp timescales that dwarf geological ages the way mountains dwarf grains of sand. But here is the crucial point. Acknowledging our limitation allows us to correct for it. Imagine compressing the entire history of the universe into a single year. The Big Bang occurs at midnight on January 1st. For months, the cosmos is a cloud of expanding gas and dust, gradually cooling, gradually clumping under gravity's patient pull. The first stars ignite in late January. The Milky Way forms in May. Our sun does not appear until early September. The universe is already 2/3 through its calendar year before our particular star begins to shine. Now the pace accelerates as we approach our own moment. The Earth forms in the second week of September. Life appears by the end of the month. Simple, single-celled, but unmistakably alive. For all of October and November, life remains microscopic. Complex multicellular organisms do not emerge until mid-December. Dinosaurs appear on Christmas Day and are wiped out on December 30th. All of recorded human history, every empire, every invention, every war and peace and work of art occurs in the final 14 seconds before midnight on December 31st. We are creatures of the last heartbeat, trying to comprehend the entire year. This is why we build monuments. This is why we carve in stone, bury time capsules, write forever in wedding vows. We crave permanence because we cannot bear the alternative. We want the universe to remember us because we cannot bear to be forgotten. But the universe does not care about our preferences. Physics proceeds regardless of human longing. And here is where the correction begins to matter. Once we know that our intuitions systematically fail at cosmic scales, we can deliberately override them. We can use mathematics where imagination falls short. We can reason our way to truths that feeling will never reach. The universe is not eternal. The stars will go out. The cosmic fire is burning through its fuel right now, in this very moment, as you read these words or hear this voice. What seems permanent is merely slow. What feels like forever is merely long. And long is not forever. The question is, what happens when the fire goes out? What are the possible endings that physics permits? We have spoken of equilibrium and cooling without yet examining what these words mean at cosmic scale. 3 fates await the universe, 3 possible endings that the laws of physics allow. It is time to build the framework that will make them comprehensible. Imagine, if you will, throwing a ball straight up into the air. This is not a metaphor. It is a model, a way of understanding cosmic destiny through something your hands have done 1,000 times. The ball leaves your palm, rises, slows, stops for an instant at its apex, and falls back down. Gravity wins. The ball returns to Earth. Now imagine throwing harder, much harder. The ball rises higher, takes longer to slow, reaches a greater apex, but still falls back. Gravity still wins. It always does, provided you remain on Earth with ordinary human strength. But what if you could throw harder still? What if you had access to some impossibly powerful arm, or more practically, a rocket? At a certain speed, roughly 11 kilometers per second, which we call escape velocity, the ball would not fall back. It would rise forever, slowing but never quite stopping, sailing off into interplanetary space, leaving Earth's gravitational influence behind. 3 outcomes then for our thrown ball: fall back, escape at the boundary, or sail away forever. The universe faces the same 3 fates. At the Big Bang, roughly 13.8 billion years ago, everything that exists was compressed into a state of unimaginable density and temperature. Then it began to expand, not an explosion into pre-existing space, but an expansion of space itself, carrying matter and energy outward in all directions. This expansion continues today. Every distant galaxy we observe is moving away from us, its light stretched by the expanding space between us. The question, the fundamental question that determines the fate of everything, is whether this expansion will continue forever or eventually reverse. If the universe contains enough matter, gravity wins. Like the gently thrown ball, the expansion slows, stops, and reverses. Everything that flew apart begins to fall back together. Galaxies approach rather than recede. Space contracts rather than expands. The temperature rises The density increases. Eventually, all of cosmic history runs backward toward a final singularity, a point of infinite density where space-time itself ceases to make sense. This is the big crunch. It is dramatic. It is violent. It is not our fate. If the universe contains precisely the right amount of matter, no more, no less, expansion continues forever, but approaches a kind of cosmic standstill. Like a ball thrown at exactly escape velocity, the universe expands eternally, but ever more slowly, asymptotically approaching a final state of maximum dispersal. But there is a third possibility, and it is the strangest of all. What if the ball, having left your hand, began to accelerate? What if, instead of slowing under gravity's pull, it sped up, rising faster and faster, defying everything you thought you knew about how objects move through space? In 1998, two teams of astronomers set out to measure how fast the universe's expansion was slowing down. This seemed a straightforward task. Observe distant supernova, exploding stars whose brightness can be calculated with precision, and use their apparent dimness to determine their distance. From distance and recession speed, calculate the deceleration. Write the paper. Collect the citations. Move on. What they found was the opposite of what everyone expected. The expansion is not slowing down. It is speeding up. The universe is not merely flying apart. It is flying apart faster and faster with every passing moment. Something is pushing. Something is accelerating the expansion against gravity's pull. We do not know what this something is. We call it dark energy, a name that confesses our ignorance more than it explains anything. Roughly 68% of all the energy in the cosmos consists of this mysterious something, and we have no idea what it actually is. We named our ignorance and moved on. The universe does not wait for us to understand. Now, if dark energy behaves in a certain way, if its repulsive effect grows stronger as space expands, then the third fate becomes terrifying. Expansion accelerates without limit. Space eventually expands faster than anything can hold together. First, galaxies are torn apart, their stars scattered. Then solar systems disintegrate, then planets, then atoms themselves. Even the fabric of space-time shreds. This is the Big Rip, the universe literally coming apart at the seams. But current evidence suggests dark energy is constant. Its repulsive pressure does not grow. In that case, we avoid the rip. Space expands, but not catastrophically. Atoms hold together. Stars and planets remain bound. What we get instead is the third fate, heat death. And heat death, despite its dramatic name, is not a death by heat at all. It is a death by cold, by stillness, by the ultimate, inescapable triumph of entropy. Think again of the cup of tea. When it was hot, it could do things. Warm your hands, steam your glasses, transfer energy in useful ways. As it cooled, it lost that capacity. Once it reaches room temperature, it reaches equilibrium. The tea has the same temperature as its surroundings. No gradients remain. No flows of energy are possible. Nothing interesting can happen anymore. The universe is heading for cosmic room temperature. Not an explosion, not a collapse. Just the slow, inexorable spread of energy toward uniformity, continuing forever, until no differences remain to exploit, no processes can occur, no change is possible. The cup of tea completes its cooling, but how long does this take? What happens along the way? We know our destination now. Equilibrium, stillness, the heat death. But understanding the destination is not the same as understanding the journey. What disappears first? What lingers longest? What is the timeline of ending? These questions lead us into the deeper mechanics of cosmic fate, the heat. Death is not a single event. It is a sequence of endings, a cascade of permanent losses stretching across timescales so vast they strain the meaning of the word number. We shall trace this timeline now, step by step, and make no mistake. What we are tracing is the future history of everything that exists. The first milestone is the end of star formation. Stars are born in clouds of gas and dust, vast nebulae spanning dozens of light years, slowly contracting under their own gravity until the pressure and temperature at their cores ignite nuclear fusion. This process has been ongoing for nearly 13.8 billion years, ever since the first generation of stars lit up a dark universe a few 100 million years after the Big Bang. But the gas is running out. Every star that forms removes matter from the available supply. Some of that matter is returned when stars die, expelled in stellar winds, scattered by supernovae. But not all of it. Heavy elements sink into white dwarfs and neutron stars. Material falls into black holes, never to return. With each generation, there is less raw material for the next. The universe is not infinitely wealthy in hydrogen and helium. The accounts are being depleted, and in approximately 100 trillion years, that is, 100 trillion years from now, the last star-forming gas clouds will have collapsed into their final stars. After that point, no new suns will ignite. 100 trillion years sounds impossibly remote, and yet, consider, it is only 10,000 times longer than the current age of the universe. If cosmic history so far is a single heartbeat, the era of star formation has roughly one more day remaining. We are closer to the beginning than we usually imagine. After star formation ends, the existing stars continue to burn, but they cannot burn forever. Large stars live fast and die young, exhausting their fuel in mere millions of years. Medium-sized stars, like our Sun, last billions of years. But the longest-lived stars, the red dwarfs, small and miserly, burning their hydrogen with exquisite frugality, can shine for trillions of years. The last red dwarf will gutter out approximately 1 quadrillion years from now. When it does, the age of starlight ends. Forever. Imagine a forest where trees grow from seeds. Each tree draws nutrients from the soil. When it dies and falls, some nutrients return, but some are locked away in wood that does not fully decompose. Gradually, over millions of years, the soil is depleted. Fewer seeds germinate. The trees grow thinner, smaller, sparser. Eventually, no new trees sprout at all. The existing trees live out their long lives, some for centuries, if they are ancient redwoods, but no replacements are coming. When the last redwood falls, the forest age ends. The universe's stars are that forest. The gas clouds are that soil. And the last red dwarf is the final flickering remnant of an age of light that began shortly after the Big Bang and will continue for a time we cannot intuitively grasp, but will not continue forever. After the last star dies, the universe goes dark. Not entirely dark, there will be remnants. White dwarfs slowly cooling, radiating the last of their stored heat into the void. Neutron stars spinning down, their magnetic fields dissipating over billions of years. Black holes drifting through space, invisible except for the occasional unfortunate matter that strays too close. But the era when nuclear fusion lit the cosmos like 100 billion trillion candles, that era ends. The process that forges heavy elements, that powers planetary systems, that makes the chemistry of life possible, gone. No more stellar nurseries, no more supernovae, no more new stars, ever. For all of remaining time, the universe passes from construction to maintenance, and then, eventually, from maintenance to silence. But we have not yet reached the deepest loss. The stars are gone, yes, but matter remains. Planets, though frozen and dark, still exist. The elements, though unilluminated, endure. Surely something survives. We shall see that even matter is not eternal. The next chapter takes us to the edge of existence itself. After the last star fades, two things remain in the universe: ordinary matter and black holes. Let us consider each in turn. Ordinary matter, the protons, neutrons, and electrons that make up every atom, every molecule, every rock and planet, and frozen remnant of every civilization, was once thought to be eternal. Individual objects might change form, ice melts, wood burns, organisms decay, but the fundamental particles themselves seemed permanent. Protons, in particular, appeared absolutely stable. Nothing could destroy them. This may not be true. Modern particle physics suggests that protons, though extraordinarily long-lived, may not be immortal. The same theories that successfully predict other particle behaviors indicate that protons should decay, transforming into lighter particles and radiation, over timescales so long that we have not yet observed a single instance, despite watching enormous numbers of protons in underground detectors for decades. The current experimental lower bound is roughly 10 to the power of 34 years per proton. That is a 1 followed by 34 zeros. But theory suggests the actual lifetime may be around 10 to the power of 37 years, still beyond our experimental reach, but finite. If protons decay, then over timescales of 10 to the power of 37 years, every atom that ever existed will dissolve. Every planet will sublimate into radiation. Every monument, every fossil, every frozen remnant of every living thing throughout cosmic history, gone. Not merely destroyed, but unmade at the most fundamental level. Nothing built from ordinary matter can survive this dissolution. The universe's material history erases itself, leaving only radiation spreading ever thinner through expanding space. But black holes survive longer. This seems paradoxical. Black holes are regions where gravity has become so intense that nothing, not even light, can escape once it crosses the event horizon. They are cosmic vacuum cleaners, swallowing everything that comes too close, growing larger with each meal. They seem eternal. They seem inescapable. They seem like nature's permanent prisons. In 1974, a calculation united quantum mechanics with general relativity for the first time and revealed that black holes are not permanent. They are not even fully black. The calculation showed that at the event horizon, the boundary beyond which escape is impossible, something strange happens. Quantum mechanics tells us that empty space is never truly empty. It seethes with virtual particle pairs, briefly popping into existence and then annihilating each other before they can be observed. Normally, this makes no difference to anything, but at the event horizon, gravity can separate these pairs before they annihilate. One particle falls into the black hole, the other escapes. The escaping particle carries energy away. That energy must come from somewhere. It comes from the black hole itself, from its mass, which is equivalent to energy by Einstein's famous equation. The black hole shrinks ever so slightly with each escaped particle. Over time, the black hole evaporates. This process is extraordinarily slow. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate, a 1 followed by 67 zeros. A supermassive black hole at the center of a galaxy, containing billions of solar masses, might endure for 10 to the power of 100 years. But eventually, every black hole evaporates completely. The last one winks out of existence in a final burst of radiation, and the universe contains nothing but that radiation. Photons and other massless particles spread through ever-expanding space, growing ever colder, approaching but never quite reaching absolute zero. The universe has more time than we have concepts to describe. 10 to the power of 100 years is called a googol. It is larger than the number of atoms in the observable universe. It exceeds not just intuition, but metaphor. If every atom in every galaxy were a separate universe, each containing as many atoms as ours, the total number of atoms would still not reach 10 to the power of 100. Some numbers defeat imagination entirely. We simply have to acknowledge them and move on. What remains after the last black hole evaporates? Nothing meaningful, nothing structured, nothing that could be called an object or an event. The final state is not nothing. That would at least be interesting. It is something far stranger. Existence without occurrence. Space continues. Time continues. Radiation persists. But the radiation is so diffuse, so evenly distributed, so utterly lacking in gradients or structure that nothing can happen. No processes can occur. No change is possible. This is the heat death. Not destruction, but dissolution. Not ending, but eternal aftermath. And yet, a question presses. A question that physics alone cannot answer, but that physics makes urgent. If this is what awaits, what was the point? Why does the universe go to all the bother of existing if it must end in eternal, unchanging equilibrium? What does it mean that everything that ever happened, every civilization, every love, every thought, every question asked and answered, will leave no trace? This is not a scientific question. It is a philosophical one. And answering it requires we reconsider not just the ending, but the time before it. Not just the silence, but the sound it will contain. We have traced the timeline. We have walked through the sequence of endings, the last star formation, the final starlight, the decay of matter, the evaporation of black holes, and arrived at the heat death, eternal equilibrium, cosmic room temperature, existence without occurrence. It is reasonable at this point to ask the question that has been gathering force since we began. If all of this awaits, what does anything mean? If everything ends in eternal cold, if all evidence of everything that ever happened must ultimately dissolve into diffuse radiation, spreading through infinite, expanding space, then why does the universe go to all the bother of existing? What is the point of building, striving, loving, thinking, if the final state erases all trace of these activities? This question feels devastating. It is meant to feel devastating. And yet, as we shall see, it contains its own answer, though reversed in a way that transforms everything. Consider two candles. The first candle burns forever. It has infinite fuel. Its flame will never gutter, never dim, never go out. You can watch it now, or you can watch it tomorrow, or you can watch it in 1,000,000 years. It makes no difference. The flame will be identical whenever you choose to attend to it. The second candle burns for exactly 1 hour. When you light it, a timer begins. 60 minutes later, the flame dies forever. It cannot be relit. The fuel, once consumed, is gone. Here is the question: which flame matters more? Most people, when they pause to consider it honestly, recognize that the 1 hour candle is precious in a way the eternal candle can never be. The eternal flame inspires complacency. Why attend to it now, when it will burn identically forever? There is always later. There is always tomorrow. The infinite candle makes no demands on our attention, because our attention makes no difference to it. But the 1 hour candle is different. Its light is irreplaceable. Each moment you spend watching it is a moment that will never recur. When the flame dies, that light is gone from the universe permanently. The temporary candle demands presence. It earns attention. It matters precisely because it will not last. The universe, it turns out, is the 1 hour candle. We have been assuming, without quite realizing we were assuming, that meaning requires permanence, that things only matter if they endure, that significance is measured in duration. But this assumption, examined carefully, inverts the actual relationship between meaning and time. Permanence does not create meaning. Permanence destroys meaning. If the universe lasted forever, if stars burned eternally and galaxies shone without end, then no moment would be special. There would always be more moments, identical in their infinite availability. Nothing would be rare. Nothing would be urgent. Nothing would demand attention now rather than later. Eternity breeds indifference because eternity makes everything replaceable, but impermanence creates preciousness. The sunset is beautiful, partly because of its colours. Yes, the scattering of light through atmosphere, the warm hues of the descending sun. But it is beautiful mostly because it ends. The colours deepen, shift, fade, and are gone. That passage is essential to the beauty. An eternal sunset would be wallpaper. A fading sunset is art. The universe is a sunset on an unimaginable scale. Every star that burns is unrepeatable. Every configuration of matter that exists in this moment, including the configuration that is you, reading or hearing these words, will never recur in all of cosmic history. The universe will never again be arranged exactly as it is arranged right now. This moment is unique, not because of cosmic planning, not because of divine intention, simply because of physics, simply because the particular arrangement of particles that constitutes this instant has never occurred before and will never occur again. That is not a diminishment. It is an elevation. We exist during what cosmologists call the stelliferous era, the age of stars. This era began shortly after the Big Bang and will continue for perhaps another 100 trillion years. During this time, the universe is lit, complex, capable of supporting observers who can look up and marvel at what they see. Compared to the eternal darkness that follows, the trillions upon trillions upon trillions of years when no stars shine and no meaningful structures exist, the stelliferous era is a flickering instant, a spark, a brief candle flame in an infinite night. You are alive during the flicker. Think about what that means. You are not living at the end of cosmic history. You are not witnessing the universe in its dotage, running down toward inevitable death. You are here at the beginning, in the opening scene, the first act, the morning of a story that will mostly consist of empty afternoon and endless night. The age of light, relative to what comes after, has barely started. We are among the earliest observers the universe has ever produced. We are witnesses to the dawn. This is not ordinary. This is extraordinary. The heat death closes off one kind of meaning forever, meaning that depends on permanence, on lasting, on being remembered by a cosmos that itself endures. If that is the only kind of meaning you recognize, then yes, the heat death is nihilistic. It renders everything pointless, but there is another kind of meaning that arises from existence rather than duration, from being rather than lasting. This kind of meaning the heat death cannot touch. Indeed, it amplifies it. because everything ends, everything matters, because nothing is permanent, nothing is negligible, because the flame will die. The light is precious. This is not consolation offered to soften a harsh truth. This is the truth itself, properly understood. But a deeper question remains. We have found meaning in impermanence, but why does complexity exist at all? If the universe trends toward equilibrium, toward the even distribution of energy, toward the heat-death, how did stars, planets, and minds arise in the first place? How can temporary order emerge from a cosmos that is, overall, running down toward disorder? The answer reveals something astonishing. The very process that guarantees our ending is the process that made our existence possible. Here is the deepest integration, the realization that transforms how we see not just the ending, but our relationship to it. We exist because the universe is dying. This sounds paradoxical. It sounds like poetry dressed up as physics. But it is neither paradox nor poetry. It is thermodynamics, properly understood. The second law tells us that entropy, the measure of disorder, of energy's dispersal, tends to increase in any closed system. This is the law that governs our cooling tea, our dying stars, our universe sliding toward heat-death. Entropy increases, order dissolves, differences even out. But here is what most people miss. Entropy can decrease locally while increasing globally. Consider a waterfall. Water flows from high to low. This is entropy increasing, energy dispersing, the universe running down toward equilibrium. But in that flow, a mill wheel can turn. Work can be done. Complexity can be powered. The falling water enables the wheel precisely because it is falling, because energy is moving from a state of higher concentration to lower concentration. If the water were already at the bottom, if equilibrium had been reached, no mill could operate, no work could be extracted, no complexity could be powered. The universe is a waterfall. Life is a mill wheel. We exist in the falling, powered by the flow. The sun pours energy onto Earth, low entropy, concentrated, useful energy in the form of visible light. Earth absorbs some of this energy, which powers weather, chemistry, biology. Then Earth radiates energy back into space, high entropy, dispersed, diffuse energy in the form of infrared radiation. In that flow, in the gradient between the sun's fierce heat and the cold void of space, complex structures can temporarily maintain themselves. Cells can metabolize, organisms can grow, minds can think. All of this is powered by the cosmic falling, by the universal slide toward equilibrium. We do not fight entropy, we surf it. Life does not violate the second law of thermodynamics. Life exploits it. By taking in low entropy energy, food, sunlight, and exporting high entropy waste, heat, carbon dioxide, living systems maintain their internal order while increasing the entropy of their surroundings. We pay for our complexity by increasing the disorder elsewhere. The books balance, the law is satisfied, but this means something profound about our relationship to the heat-death. Without entropy, without the universe running down, nothing interesting could happen. A universe at equilibrium is a universe where no processes can occur, no gradients to exploit, no flows to harness, no energy available for work. It would be static, unchanging, dead in the deepest sense, not because it lacked matter, but because it lacked difference. The very process that guarantees our eventual dissolution is the process that made our temporary existence possible. Think about what this means. The heat. Death is not merely our destroyer, it is our enabler. The same cosmic cooling that ensures all complexity must eventually fade is what created the conditions for complexity to arise in the first place. We are not fighting against the current of entropy. We are riding it like surfers on a wave that will eventually break upon the shore. We could not be here if the universe were not cooling. If the cosmos had begun at equilibrium, we would never have existed. There would be no stars to forge heavy elements, no temperature differences to power chemistry, no energy gradients to exploit for metabolism, no possibility of observers who could look up and ask why they exist. Our existence and our ending have the same source. We are children of the cooling. Consider your own body. Right now, as you read or listen, you are maintaining a complex structure through continuous energy flow. You ate food, concentrated chemical energy, and your metabolism is converting it into heat, motion, thought. That heat radiates from your skin into the surrounding air. You are a temporary eddy in the entropic stream, maintaining your pattern for a few decades by exporting disorder into your environment. When you eat breakfast, you are participating in the cosmic flow from hot to cold. When you warm a room with your body heat, you are contributing to the entropy of the universe. When your metabolism finally stops, the atoms that were temporarily, you will rejoin the general dispersal, continuing the journey toward equilibrium that began at the Big Bang. This is not depressing. This is awe-inspiring. We are not anomalies in a dying universe. We are expressions of it. We are what happens when a universe running down toward equilibrium generates temporary pockets of complexity along the way. We are the mill wheels turned by the cosmic waterfall. People often view entropy as the enemy, as something life resists, opposes, struggles against. This is backwards. Entropy is the engine. Life is the wheel. Without entropy, increase, no energy gradients. Without energy gradients, no processes. Without processes, no existence. We should thank entropy, not curse it. The heat death made us possible by creating the flow we ride. One mystery remains. Why does any of this exist at all? Why is there a universe capable of producing beings who can trace its history from Big Bang to heat death, beings who can understand the very processes that created them and will eventually end them? This question leads us beyond integration toward wonder, not the wonder of not knowing, but the deeper wonder of knowing and being astonished by what we know. Look at your hand. That hand is made of atoms, carbon, hydrogen, oxygen, nitrogen, and traces of heavier elements like iron, calcium, and phosphorus. Those atoms were forged in the nuclear furnaces of stars, billions of years before our sun was born. The carbon in your cells was created when helium nuclei fused together in the cores of red giant stars. The iron in your blood was produced in the final moments of massive stars, just before they exploded as supernovae. The calcium in your bones, the phosphorus in your DNA, the trace metals that enable your enzymes to function, all of it was cooked in stellar fires and scattered across space when those stars died. You are not made of the same stuff as stars. You are made of stars, literally, physically, atomically. This is not poetry. This is nuclear physics. And here is the strange thing. Those stellar atoms gathered by gravity into a planet, further concentrated into organic molecules, assembled through billions of years of evolution into the particular pattern that is you. Those atoms are now wondering where they came from. We are the universe contemplating itself. This is not mysticism dressed up as science. It is the straightforward implication of what we know about cosmic history. The cosmos began as hydrogen and helium, produced in the Big Bang. Stars processed that primordial material into heavier elements. Those elements were scattered when stars died, gathered into new solar systems, incorporated into planets, and, at least once, on at least one planet, assembled into structures complex enough to ask questions about their own origins. The universe, through beings like us, has developed the capacity to know itself. Consider how improbable this is. The cosmos was under no obligation to produce consciousness. Nothing in the laws of physics required that matter should eventually arrange itself into patterns capable of thought. The processes that led from Big Bang to you, stellar nucleosynthesis, planetary formation, prebiotic chemistry, the origin of life, billions of years of evolution, could easily have gone differently at countless junctures. Minds were not guaranteed. Curiosity was not inevitable. Understanding was not predestined. And yet, here we are. Here you are, a temporary arrangement of stellar ash, briefly conscious, capable of comprehending the 14-billion-year history that produced you and the trillions of years that will follow your dispersal back into the cosmic flow. Imagine, if you will, the ocean becoming conscious in a single wave. For a moment, just a moment, relative to the ocean's vast duration, that wave is aware. It knows itself as water. It can contemplate the water cycle, the chemistry of H2O, the physics of tides. It understands where it came from and where it is going. And then it crashes upon the shore, loses its form, and rejoins the unconscious sea. We are that wave. The atoms that think in you were not thinking a century ago and will not be thinking a century hence. For this brief interval, this flickering instant in cosmic time, the universe knows itself through you. That is not ordinary. That is staggering. Some people, contemplating the vastness of the cosmos and the brevity of human existence, feel diminished. We are so small, they think. We are so temporary. The universe is so vast and so indifferent. What can we possibly matter? But this inverts the significance of our situation. Yes, we are small. A single human life spans roughly 80 years on a planet 4 billion years old, in a universe 14 billion years old, and destined to continue for timescales that defeat comprehension. By any measure of duration, we are negligible. But smallness and brevity make our existence rare. Rarity makes it precious. And our capacity to comprehend the vast tiny creatures holding billions of light years in our minds makes us strange and wonderful indeed. The universe does not care about us in the way we might wish it cared. There is no cosmic parent watching over human affairs, no celestial plan in which we play a significant role. But the universe does care through us. We are the universe caring. We are matter and energy become capable of love, curiosity, joy, and grief. The indifference of the cosmos is overcome not by external intervention, but by our existence within it. Eventually, all minds will fade. All understanding will cease. The universe will continue its cooling without observers to marvel at it, without consciousness to ask why it exists, without any being anywhere capable of wonder. The window is closing. In cosmic terms, it has barely opened. But right now, the window is open. Right now, the universe contains at least one place where matter has arranged itself into patterns that can contemplate their own existence. Right now, stellar ash is wondering about stars. That we can understand this at all is remarkable. That we can trace our atoms back to supernovae and forward to the heat death, that we can hold in our minds the entire arc of cosmic history, is a gift that physics gave to itself. One question remains: how do we carry this understanding forward? What does it mean for how we see the ordinary world, the cup of tea on the desk, the stars overhead, the brief and precious time we have. We began with a cup of tea. Let us return to it now, but see it differently. The cup sits on your desk, cooling. An hour ago, it was hot enough to warm your hands, to steam your glasses, to perform the useful work of transferring energy to your cold fingers. Now it has reached room temperature. It has equilibrated with its surroundings. Nothing interesting can happen to it anymore. Thermodynamically speaking, it is finished. But look closer. The water in that cup was forged in stellar cores, hydrogen and oxygen nuclei fusing under unimaginable pressure and temperature in stars that burned out before our sun was born. The atoms in the porcelain were assembled from silicon and aluminum and other elements cooked in ancient supernovae. The heat that once warmed the tea came ultimately from the sun. Nuclear fusion 93 million miles away. Light, taking 8 minutes to cross the void. Photons absorbed by the kettle element and converted to the thermal energy that boiled your water. The cup of tea is not merely cooling. It is participating in the same process that governs stars and galaxies, the universal trend toward equilibrium, the cosmic slide toward heat death. In miniature, on your desk, the fate of the universe is being demonstrated in real time. And you, holding that cup, watching it cool, thinking about what it means, you are the universe holding itself, contemplating its own fate with atoms forged in ancient stars. The cup contains the cosmos. The cosmos contains you. There is no separation between observer and observed, no boundary between self and universe. You are not in the cosmos looking at it. You are the cosmos looking at itself. This is where we arrive after our journey, not at despair, not at nihilism, but at something closer to reverence. The universe ends not with a bang, nor with a whimper, but with a silence so vast it contains all the sounds that ever were. Every song ever sung, every word ever spoken, every laugh and cry and whisper throughout all of cosmic history, all will eventually dissipate into the background radiation, spreading through infinite expanding space, diluting toward, but never quite reaching absolute zero. But here is what we understand now. Having come this far, the dissipation does not erase the occurrence. The sounds happened. They mattered. They contributed to the entropy of the cosmos in their own small way. And in that contribution, they are preserved, not as memories, not as records, but as effects, as consequences, as ripples in the fabric of space-time that continue outward forever, even as they become unmeasurably faint. The silence remembers, in the only way physics allows. Nothing is forgotten by the universe, because the universe is not capable of forgetting. It has no memory to lose, no mind to fade. What it has instead is causation, the chain of effects extending from every cause, spreading outward, thinning but never quite vanishing, encoded in the arrangement of particles that follows inevitably from the arrangements that came before. Your life leaves traces, not monuments that survive the heat death. Nothing survives the heat death in any meaningful sense, but effects, consequences. The pattern of your existence contributes to the pattern of the universe's existence, and that contribution, however small, is permanent in the only way permanence is possible. It happens, and happening cannot be undone. Tonight, if the sky is clear, go outside. Look up. The stars you see are not backdrop. They are fellow travelers, suns burning through their fuel, just as you burn through yours. All of us temporary patterns in the cosmic cooling. All of us precious, precisely because we are temporary. That light left its sources years, decades, centuries ago, travelling through the void until this very moment when it reaches your retina and becomes part of your experience. The universe is displaying itself to itself through you. You are standing in the age of light. 100 trillion years from now, when the last star has faded, no being anywhere will see what you see tonight. The stelliferous era will have ended. The great darkness will have begun. And it will continue, not for billions of years, not for trillions, but for timescales that language cannot capture and imagination cannot approach. But right now, the stars still shine. Right now, complexity is possible. Right now, minds exist that can ask why and occasionally find answers. This moment will never recur. The particular arrangement of atoms that constitutes this instant, you reading these words, the stars overhead, the planets in their orbits, the galaxies in their clusters, has never existed before in all of cosmic history and will never exist again. You are here for it. That is not a reason for despair. That is the only reason for wonder there ever was. We are just an advanced breed of primates on a minor planet orbiting an average star in the outer suburbs of one galaxy among 2 trillion. Our lives last an eye blink. Our civilization has existed for less than the final second of cosmic history compressed into a year. We are small, brief, and seemingly insignificant, but we can understand the universe. We can trace its history from the Big Bang to the heat death. We can comprehend the processes that created us and the processes that will end us. We can ask why there is something rather than nothing, and even if we cannot fully answer, we can recognize the question's profundity. That makes us something special. That makes this moment precious. That makes the cooling cup of tea and the fading stars and the brief flame of consciousness worthy of attention and reverence and awe. The cup of tea cools, the stars burn out, the black holes evaporate, and still, for this glittering moment, we are here. That is not a reason for despair. It is the only reason for wonder there ever was. We find ourselves in a bewildering universe, vast beyond comprehension, ancient beyond imagination, destined for a silence deeper than any darkness we can conceive. And yet, against all odds, we exist. We think. We wonder. We look up at the stars and ask questions the universe has no obligation to answer. We are stardust, contemplating stardust. We are the cosmos knowing itself. We are temporary patterns in the eternal cooling, children of entropy, siblings of the stars, precious precisely because we will not last. The candle burns for 1 hour. The flame is everything.